Alright, in the last video, we revisited the old concept from Intro Physics, the concept of work, and we defined it as a force exerted on an object, dotted with the object's displacement. We said it was a scalar. We said it's the result of a dot product, so we're only dealing with the component of force that is parallel to our displacement. And we ended the video talking about the assumptions that we're making when we write this equation down. And the major assumption that we are making here is that delta r, which is a vector, is linear. And sort of by its definition, it's the line between the two positions, right? The line between the starting and finishing dots. So what I want to do today is look at a situation in which the path that is taken through a force field is not linear, right? And see what happens to the way that we calculate work. So I'm going to draw my three-dimensional axes, x, y, and z. Voila, x, y, and z. Now I'm going to define a path. So my starting position, I'm going to put it right here. My final position, I'm going to put right here. And I'm going to draw a very obvious line in between the two. Let's go from here to here. And I'm going to make that curvy, very, very curvy. Just going to make a point. There we go. And I could have drawn this anyway. We're going to talk about this very generally for all kinds of curved paths. Okay? So imagine this object moving along this path within a force field. And I'm going to say that my force can be, any kind of force. So F is defined as a function of x, y, and z. So what that means is that at any point in space, my force is going to be different. So the force will be different for any point in this entire three-dimensional space, right? So it can be pretty chaotic sometimes. You can have the force going in this direction over here. Maybe the force is really strong over here in that direction, and then it could be all over the place. But the idea is that it could be any force, right? Any force that we want to. I'm gonna erase all these because they don't look good. Okay, so we have a force, any kind of force, and I'm going to draw my position vectors. So those have arrows on them. I'm going to draw this one. This is my Ri. Always from the origin, we have to have some sort of reference point. This is Ri. And we have an RF over here. That will be RF. Let's see, I'll put it over here. RF. Now, first off, I want to show you that I could draw a straight line, my delta r. I could draw a straight line here, over here, and I could call it delta r. For sure, I can do that. Right? And I could plug that delta r. Ooh, that's awful. I could plug that delta r into my equation. Right? I can plug it up here, and I can get a value for work. Right? And I would call that an approximation of the work done along this path. And of course, it would be a terrible approximation because it doesn't really follow the path that I'm taking. Right? But what if I were to separate it into, say, 3 chunks, or three bits? Alright, so I'll take that. I got my arrows. What if I were to separate it into 3 bits? 1, 2, 3. Well, now we're getting a little better, and all of these have delta r's. These are all value delta r. Now we're getting a little better at approximating this path taken, right? And the more arrows that I use, the shorter that these arrows are, right? This is kind of the classic calculus intuition. But the shorter that these arrows are, the better approximation that it is of the curve, right? So I'm going to draw a bunch of little delta r's really quickly, really quickly. I'm going to start out with just one, and then make a bunch. And there you go. We have sort of a cool looking dragon tail here, and all of these little arrows, they have a length delta r, or magnitude delta r. Alright, all of these have the same magnitude delta r. Right. So I'm going to write an equation for work now, and I'm going to take into account all these little delta r's and the f's. So imagine we have this object moving through this space, and the force is different, right, for each little bit delta r, right, for each little bit. So we have this equation, or we have this expression f of x, y, z, and I'm going to dot it with my delta r's. So dot delta r. And I'm going to take the sum of all of these, because remember the forces are different. Even though the delta r's, their directions are different, and the force has different value and direction depending on whatever force we decide to do. So all of these are going to have different values for work, and the sum of all of them represents the total amount of work done along the path. So drawing the sum thing, it's really hard to draw. 1, 2, 3, 4. Nice. So the work done is equal to the sum of all of the forces dotted with all of the delta r's. Right? Now I'm going to take the classic calculus intuition again. I'm going to say that the smaller that these delta r's get, the better the approximation is of the curve, and we want to go for the gold, the best approximation possible. So I'm going to say that these delta r's are going to go to 0. In essence, I'm taking a limit. Okay, so the limit work is equal to the limit as delta r goes to 0. Ooh, it's a little unbalanced. Delta r goes to 0 of the sum. Concentrate. Oh, here we go. Of the force in terms of x, y, z. Remember, it could get crazy. Dotted with all these delta r's. Alright, and if you've taken calculus before, any kind of calculus, you know that we're basically building up the idea of the integral. So I'm going to rewrite this integral. The work is equal to the integral of f of x, y, z. There's a vector dotted with dr. And I'm going to get to that in a second, but first I want to talk about what are the limits of integration on this integral. Well, since we're in terms of r, we're taking the integral r, and once we take the integral, we'll have some r values here. So the integral is going to be taken from our original position to our final position. So I'm going to write that down here, r in the best way possible, r f. Alright, now what's left is how do we interpret this little dr here? Well, the dr, the way that it was explained to me and the way that I understand it is that it's an infinitesimally small r, an infinitesimally small delta r right here. So we have many, like an infinitely many delta r's, or infinitely many dr's of infinitely small length, right? And if we take the limit of the sum of all of those, then we have what we consider to be an exact value for the path taken. Alright, so this is it. We've done it. I'm going to put a box around it to represent good work. Alright, so the work done for any force that we can possibly define or express through writing or through math, dotted with any path, no matter how curvy it can get. So it can get really crazy if we wanted to. Some complications come up when we draw loops, but maybe we'll get to that later. And it's pretty powerful stuff. We can calculate the work for anything, for any kind of force that we can define, dotted with any kind of path that we have. So I'm gonna leave you with that because it's very powerful.